Hi, my name is Nathan Farmer, and welcome to my presentation on Lab 1, the charge tapes. So, the purpose of this lab was to explore interactions between various charged and neutral objects in the real world and compare our findings to a theoretical model. So, essentially, this happened in two separate steps, the real world experimenting and computational models. So, essentially, we took Scotch tape and charged different pieces of that and saw how it interacted with other objects, and then we used GlowScript to pretty much program a visual representation of our findings. So some principles that we had to keep in mind while doing this lab was obviously Coulomb's law, which is super important because we need to know the electric force responsible behind the movements that we're seeing with these interactions, right? And then this Newton's second law, specifically for gravitational force, was also super important because we had to, you'll see in the second experiment, we had to set this equal to that electric force, right? And then finally, probably the most important thing is just properties of charged objects, so that like charges repel, opposite charges attract, and how neutral objects can get this induced dipole as a result of other charges. So for experimentation, it was pretty much two separate parts. You had the observation identification, which was the first part, and in this part, what we did was we created these U-tapes by placing, a strip of tape on top of our desk and then another one on top of that and ripping it off, and then supposedly it had some charge and we needed to identify what that charge was. So how we did this is we took three other objects, another U-tape, a neutrally charged book, and a negatively charged pen, and we saw how they interacted. So with the U-tape, with another U-tape, they repelled, so we knew it wasn't neutral. Against a neutrally charged book, it attracted, so once again we know it's not neutral. And then with a negatively charged pen, it attracts, and this tells us that because we know it's not neutral, it has to be positive, right? So then with this information, now that we know that it's positive, we want to know its exact charge though. So we take two U-tapes and suspend one, right? And then take the other one and put it under there and try to counteract the slack in the originally suspended one to counteract that gravity force on it, right? So, and then we need to measure the exact distance between the two charges when it's at equilibrium. Some assumptions that we have to make here, though, are that both tapes have, an exactly identical charge, which is not going to be the case, but it'll be close enough for this experiment, and that the electrical force can be simplified to 2-point charges because, the electrons on each one are going to be, or the charged particles on each tape are going to be interacting, but for this purpose, just the distance between them will be good enough for us. And for experimental results, this is just what I ended up getting. I took the mass and the distance between them and then used that to set the gravity equal to the electric force, and then was able to just calculate for the charge being the last variable there, got the charge, and then divided that by the charge of a singular electron to get how many electrons there were, and then actually discovered that only 0.0013% of the surface atoms gave up their electrons, which is much less than you would probably expect. And then for the coding, this was just to visualize that second part of the experiment, with the suspended tape. And how this happened was I took a function from the previous charged particles lab that we did and just passed in both tapes as the charged particle and the observed location to get that electric field, multiplied that by the charge for the electric force, calculated the gravitational force, and then drew arrows for all three of these forces to get a visual representation, as you can see here, of what of the magnitude of the gravitational force versus the electric force. And what we end up seeing is that when I pass in my own experimental values, which is in this case, is that it was actually very close to the theoretical value. In fact, only 0.4% error. And once again, we're using the same assumptions, which is why this is very surprising that it was this accurate, we're calculating the tape as a point charge and that both had identical charges. Follow-up questions though, what if electrons had positive charge and protons had negative charge? Well, now the thing about this is that it doesn't actually matter whether protons are positive or electrons are negative. It's just that same sign charges repel each other and opposite sign charges attract. And then finally, why is it important to handle the charge tapes as little as possible? And that this reason is that because of the excess charge on the surface of the tape dispersing through other surfaces, when they come in contact, it's going to lose that extra charge anytime it touches something else. And that's my presentation. Thank you so much for watching.